Hello, ladies, gentlemen, and friends. Thank you for being here for my presentation. My topic title is the Convergent Causal Consistency for Social Media Posts. I wanted to give you an overview about the organization of the presentation today. First, let me start by giving you something about the motivations and contributions of my research. I'm going to introduce the benefits of the data replication and express the different classes of consistency models. Then, consider the problem of enforcing convergent causal consistency for social media posts. Of satisfying these requirements, Causal is the protocol proposed to achieve the total system cost optimization. I present the system architecture implemented in Causal. Next, I will also provide the simulation results and discuss some interesting points. Finally, I will summarize a brief statement of the conclusions. In distributed geo-replicated system, data replication can provide fault tolerance and low latency for better availability and performance by making multiple copies on multiple sites. This could be achieved by storing appropriate replicas of the data resources at multiple geographical locations. But data consistency in concurrent reads and updates becomes an important problem when data is replicated. There are several different consistency models in distributed environments. These models represent a trade-off between the cost and convenience metrics for application programmer. Most of the large-scale distributed data storages focus on two desired features: low latency and high scalability. Causal consistency is a stronger consistency model that satisfies low latency and achieving high availability. There are two different replication strategies, including full replication and partial replication. Partial replication can help to reduce the total network transmission overheads. In this topic, we focus on the causal consistency model under partial replication for geo-replicated cloud storage. Causal consistency defines causally related write operations must be seen by all the processes in the same order, but concurrent write operations may be seen in different orders on different machines. If the two write operations are causally related, which means the one write operation comes after a read operation, that read operation returns the value of the other write operation. So let's see two examples. In figure A, a data store is not causally consistent. Two write operations in P1 and P2 are causally related because value B is the result of the computation involving the read operation to read value 8 from variable X in P2. However, P3 violates that ordering because it reads value 8 after reading value B. In figure B, the data stored is causally consistent. Write operations in P1 and P2 are concurrent. Let's move on to the motivation and the problem statement of this study. We are going to discuss the problem of convergent causal consistency for posts and comments in social media platforms. Our motivations come from the following reasons. Causal consistency preserves intuitive causal ascription. This feature is important in social networks. It improves the user experience because with it, events appear to each user in the correct order. However, the ordinary causal consistency doesn't support the convergent property on concurrent updating operations. So, update conflicts could lead to replicas having different values for the same key in key value store systems. Causal plus the consistency we call the CC plus requires that data replicas converge to the same state under concurrent updates from the different clients. Currently, the most existing CC plus protocols are based on full replication. Also, dynamic replication and placement can enhance the system availability in time-varying environments. A number of CC plus protocols have been proposed for partially replicated key value store systems. Most of them are based on static replication strategies. None of them could simultaneously satisfy the following requirements in social media systems. First, all the reply comments under a post follow causal consistency. Second, each individual post may be replicated to the other different data storage nodes. When concurrent updates to a post are made in different replicas, the comments of each replica post could be ordered in the same sequence. Third, each post would be dynamically replicated to geographically diverse data store nodes in different time periods according to the user requirements. Therefore, the objective is to devise a cost-optimized protocol to enforce CC+ for posts and comments within a data center or across data centers in the partially geo-replicated storage and satisfying the above three requirements. So, we propose the Causal protocol to achieve those requirements. Here highlights the main contributions of the Causal. Causal can achieve the CC+ for all replying comments corresponding to a post with a unique key or for different objects with explicitly happen before relationships in social applications by a key value store system. Also, Causal is adapted to dynamic replication and incorporate the CC+ across storage layer replicas and caches to reduce network transmission costs. We use an example to explain how a social media post is displayed by applying CC+ protocol on it. When an image is posted on site 1 and then replicated to site 2, later, different replying comments corresponding to this image are concurrently issued on different sites and replicated to site 1 and site 2 respectively. Afterwards, when two users, Alice and Bob, have access to this image post from the different sites, they can observe the same order of the comments under this image post. Here presents a high level of the system design of the Causal. Causal is working in a distributed one key and multiple values the data store to manage a set of the data object for social media platforms. A key corresponds to an image or a clipped post. A value presents the one comment replied to a post. Each value corresponding to one update operation. Multiple values of a key are put into a value column with the causal order. Each key or value is bound to its depends metadata. When users request access to a post object, those values in a value column will return as the result. If the replica server received an updated value VU, but some happen before the updated values are not ready, VU will not be inserted into the value column until those happen before the values are visible. The system architecture of the Causal is presented here. All the data centers are fully connected by WANs. In each data center, there are multiple web servers. Each web server manages the data access demands from one geographical region and connects to its own data server, which is called the host server of that connected web server. Data objects could be replicated and synchronized linked between the data centers or within a data center. Let's go through the more details of the system architecture of the Causal. The depends metadata element is the tuple structure. A depends tuple includes 3 entries: initial server ID, scalar timestamp, and a list of the replica server destinations. The client layout of Causal provides 3 operations for clients to post, to update, and to retrieve a data item. The storage layer also provides 3 operations to respond to 3 different operations from the client layer. Causal incorporates proactively the dynamic replication coupled with the cache control as the underlying replication strategy. COP is the cost award optimized data replication strategy proposed in 2019. Due to time limitation, we skipped the details of the catch-up replication strategy. The performance evaluations are figured out as the following. The data store is deployed in 36 area zones in closed-scene event simulator tool key. Each data center is composed of the 4 data node servers. We evaluate the catch-up for replica placement of the data objects compared to case CS of the different predetermined numbers of the replica data centers with cache control. Actually, without the called replication strategy, catch-up is equivalent to case. We vary the put rates from the 0.05 to 0.8. We use the realistic Twitter traces as the data object workload. The simulation is performed for a period of 20 days in a time slot interval of 30 minutes. The prices of the storage classes and the network services are specified based on the Amazon Web Service in 2019. Here, the table presents the results of the storage cost, network transmission cost, transaction cost, and the total system cost in different put rates. Although catch-up incurs the network transmission cost and storage cost slightly, it obviously performs of the lowest total system cost compared to case of the different number of the replica data centers. Here, the top table presents 3 different performance evaluation results. Their definitions are shown in the bottom table. Delta saving is used to show how cache improves the catch-up based on the cost improvement rate. Delta increase, which is the cost increase rate, illustrates the effectiveness of the catch-up compared to OPT solution. OPT means the underlying replication strategy runs in the optimal placement solution. The OPT solution is an optimal replication approach and is proposed in the catch-up replication strategy. It already knows that exact temporal and spatial data object access patterns in the future. Therefore, OPT solution can figure out the optimal object placement for each data object per time slot. Delta increase plot, which is the second cost increase rate, presents the comparison between the catch-up and OPT without cache control in steady states. In this study, we proposed a new cost-optimized protocol that ensures the CC plus for all the replying comments corresponding to an object with the unique key order for different objects which explicitly happens before the relationships in social applications by a one key multiple values the store system. Because of the potential of the dynamic replication strategies for system cost saving, we adapt the consistent protocol to catch up for our proposed replication algorithm called in optimize the total system costs. Due to the potential of the cache in performance benefits, we incorporate the cache mechanism into catch-up to reduce the network transmission costs. Unless anyone has anything else to add, I think that's it. Thanks for coming.